Hello, everyone. My name is Tomasz Zajkowski. I'm a molecular biologist, fascinated with all aspects of life from molecular origins to its systemic complexity. Like you all, I care deeply about life on Earth, and I'm curious about the possibility to find life beyond our planet. Did you ever think that life on Earth might be not the only kind and the universe might actually be teeming with alien life forms? I certainly did. But answering this question in a scientific way is an extremely complicated endeavor. But we as human species, we like challenges. And this is what brought us here together. To integrate, to learn, and to work together to answer the most fundamental questions humanity ever had a chance to ask. How did life originate? How did life evolve? What is the future of life? And are we alone in the universe? These questions lie at the core of the scientific discipline of astrobiology. In my scientific career, I always valued the aspects of collaboration and education. And these values lie also at the core of the Polish Astrobiology Society that we started building just 1 year ago. As the president of the society, it is my great honor and pleasure to welcome you all on our first conference organized by the Polish Astrobiology Society. From this place, I'd like to thank all the organizers that worked really hard to make this conference possible. And I hope that you all will enjoy what we planned for you for the next 3 days. I am very happy to see that so many people registered for our first conference, and there will be more. We have people joining from 17 different countries, a true display of international diversity. Today, we will begin with the lecture by Jason Dworkin, a senior scientist at NASA Goddard Space Flight Center, and the chair of the session will be Rafał Szabla from the Department of Physical and Quantum Chemistry of Wrocław University of Science and Technology. The lecture will be followed by the poster session that can be accessed by clicking on Expo on your left side of the screen. Authors of the posters will be there, and they will be ready to answer your questions using chat. So please remember, use chat to ask questions. After the poster session, we will have a networking event. To join it, please click on Networking, the button on the left. You will be randomly connected with different attendees of the conference, and you will have about 3 minutes for conversation before you will be reconnected with another person. If you have any questions, please ask them on the main chat, and we will try to answer them as soon as possible. But before we start, I'd like to spend just 3 more minutes introducing you to the Polish Astrobiology Society. From the very beginning, the goal of the society was to bring together scientists actively working in the field of astrobiology and people that wish to join our effort in understanding life in the universe and help humanity explore the vastness of space. We also see the science of astrobiology as a beautiful educational platform, and we happily support any educational initiatives. To teach astrobiology and to help introduce the science of astrobiology to the general public, we have built a webpage, AstroBioPL, where we collect educational materials and we explain different aspects of astrobiology. We are also present on social media, providing you with news and opportunities in astrobiology, so please join us on Facebook, YouTube, Twitter, Instagram, even TikTok. As part of our regular activities, we are meeting for weekly seminars, and once a month we organize panel discussions. During these discussions, scientists that specialized in specific field of astrobiology, they talk about subjects like the origin of life, extremophiles, synthetic biology, or space medicine, just to list a few. You will find the recordings of the previous discussions on our YouTube channel. There, you will also find interviews with Polish astrobiologists and recordings of past seminars. Recently, we have introduced a new custom. One seminar a month is now held in English, so please contact us if you would like to present in English. We collaborate with foreign research institutions, so if you are interested in joining our efforts, please contact us via the contact form on the webpage AstroBio.pl. Here, I will end my introductions, and once again, I'd like to welcome you all and wish you incredible time during the next 3 days of learning, discussing, and integration. And now I officially open the first Life and Space conference organized by the Polish Astrobiology Society. Enjoy.
Hello, everyone. It's really nice to welcome you at our first Polish Astrobiology conference. That was a really nice introduction to the activity of our society. So I hope that you will be interested in following us and learning more about our activities. And of course, we are also interested in welcoming new members from abroad. Once per month, we also hold meetings in English, so please do contact us. And thank you, Tomasz, for saying more and introducing our society. So today, it is really my pleasure to introduce to you our plenary speaker, who will open the conference, Dr. Jason Dworkin, who is a senior research scientist and group leader at the NASA Goddard Space Flight Center. Jason has been there for almost 20 years, which is quite a lot of time. And he started there in 2002 as a research scientist, while currently he's the head of the Astrobiology Analytical Lab. So you might think that actually analytical lab and astrobiology is not so much related to space flights, but you will see today that it is actually very, very closely related to this. And Jason's work is really focused on analyzing various samples, including samples which are returned from, in this particular case, the asteroid Bennu. In the past, he was also interested in studying astrochemically or astrophysically relevant laboratory ices and also organic and chiral molecules and their presence in other meteoritic materials which reached our planet. I think it is also very important to mention that Jason has very exciting and fascinating history in terms of prebiotics chemistry, studying prebiotic chemistry and astrobiology, because he did his PhD with Stanley L. Miller, who really was one of the first researchers interested in studying prebiotic chemistry and the origins of biomolecules on Earth. So he did his PhD at UC San Diego in 1997, and then he worked for 5 years at the NASA Ames Research Center until 2002. So I guess I shouldn't take more of your time, and Jason, take it away. We are really looking forward to the fascinating science and interesting news about the OSIRIS-REx mission to the asteroid Bennu.
Thank you for the honor of being able to speak at this first conference and this really exciting program that you've constructed. So let me get going. If you can put my charts up. Excellent. Let's see. So I'll be talking about the OSIRIS-REx sample return mission from Asteroid Bennu, and it is in many respects an astrobiology focused mission. So let's see if this will work. Like many of you, I'm interested in the ancient Earth. And so here's a cartoon from the webcomic XKCD, which hopefully you follow because it's often relevant. So nearly 4.5 billion years ago, Earth had liquid water. All the crust older than 3.5 billion years has been recycled in the mantle by subduction. That is, of course, the process of refreshing the surface of the planet, or plate tectonics, which could be fundamental to enabling life. Recycles the crust and erases the geologic record. So 1 billion years, the stratigraphic record, memory of the hills is forever lost to us. What was it like here 4 billion years ago? Earth, what secrets do you have? Come closer. I'll never tell. The Earth is relatively silent on this. All we have are these stupid tantalizing zircons, which are very hard crystals that we have recovered and from 4.2 billion years ago, and record that there was in place an ocean enough to form these crystals, and scars on the face of the moon, which tell us of the impact record that there was bombardment during and shortly after the accretion of the Earth by asteroids and comets. So we can look at these meteorites, which are the fragments of asteroids and comets that land on the Earth, to understand what the chemistry was like on this period of time. But meteorites are not well connected to the parent, and they quickly become contaminated. And so, to remind you, we come from the stars. Here's the star-forming region of the intersection of the diffuse medium and a dense molecular cloud, out of which stars and planets form. They create in these protoplanetary disks. And then eventually you get a flare disk out of which planets can form. And these planets go through their own internal evolution, as our solar system did from perhaps the Grand Tack, where the giant planets moved and then upset the structure of the solar system, perhaps relating to the moon-forming impact that set our modern Earth in motion, into the modern solar system, which this is a commonly shown picture that is, of course, grossly not to scale. For fun, there's the 1 pixel moon that you can play with. You get a sense for the scale of the solar system if you don't think about that often. And of course, what we're interested in here is the origin of life on Earth or elsewhere. And so here's the often shown picture of the ancient Earth. And this is, of course, to remind us that all biology on Earth is connected, including, of course, you, connected to all of your close ancestors, because we all use the same type of molecular machinery and the same type of chemistry. And so we can look at these astrochemical processes that I just quickly went over, the diffuse medium, the dense cloud, star and planet formation, and recycles back through stellar death and mass ejection. And we can learn about these areas up here through remote observations and simulations. And we can learn about the ancient Earth or other primitive body through laboratory simulations or modeling. But you can actually do lab analyses on materials you can get that witnessed these reactions in planet formation in early bodies in your laboratory. So, for example, you can observe these distant locations with spectroscopy, which is a great technique. So here's, for example, some infrared spectra. The top trace is water and carbon dioxide in the gas phase. You can clearly tell it's different on the absorption on this axis from the same compounds frozen in ice. Same material, you can clearly see the difference in the spectral lines. If you can rearrange the atoms into a different molecule, methanol instead of water and CO2, it's also even different. But when it comes to complicated species, like an apple and an orange, they are functionally the same. It's very hard to compare apples and oranges unless you can bring them into the laboratory and investigate the apples and oranges on the chemical level in for example, chromatography. So in this case, this is a physical separation on a liquid chromatographic column. And then this is intensity of the abundance of sugars. And so you can tell that apples and oranges have a different glucose and fructose concentration, for example. And so when you look at these processes, and you can go to the same level of detail as you can dissecting apples and oranges by bringing the samples back in the laboratory and understanding them. And there's a wide range of ways to get extraterrestrial samples, ranging from things like people who do meteor hunting for profit and tend to be very poorly documented and tend to be very contaminated, to university consortia who go to some of the deserts of the world or look for recent falls, such as the Amhasasita that fell in Sudan and was collected by these university students and professors. And you can compare that against soil that you can collect from the area. Better than that are the U.S. and Japanese expeditions to Antarctica to look for meteorites. You can compare that to the relatively clean Antarctic ice. And they're relatively easy to find because meteorites tend to be black and ice tends to be white. And there's a whole geologic reason why meteorites tend to concentrate in certain areas. Even better than that, you can go to a specific asteroid and get a specific sample in a well-documented, understood contamination environment and bring that back and analyze it. So this is part of the continuum. And all of these different samples of meteorites examine different regions of the solar system, different environments. So for example, in the main asteroid belt, you have a range of different kinds of asteroids based on their arcane spectral types. And the meteorites that you analyze are representative of these different types and or the different regions inside of an evolving planetary body. And then these are reflected in this taxonomy of different types of meteorites. You've probably have heard of the famous Murchison meteorite. It's a CM2, named after the archetype, which is Mackay, which is named after the closest post office to where that sample is recovered. So it's another one of these arcane nomenclature systems. And there's been an increasing study, some of it by my laboratory, looking at the different kinds of meteorites and what their chemistry can tell us about the early solar system. And I'll briefly advertise some of the work in my laboratory, where we look at a range of different types of meteorites and try and look at a number of compounds, including in this case amino acids. And we can see that the structural diversity of the amino acids, in this case the C5 amino acids, seems to be to correspond with the type of alteration, level of water versus level of heat in the parent body, as well as the total abundance of amino acids, and this is a log scale. So you can say a lot by looking at these sorts of organics, both as far as cosmochemistry, as well as looking at, well, gee, which are the ones that tend to favor the astrobiologically relevant amino acids, and of course, the emergence of chiral asymmetry in amino acids and other compounds, and meteorites, which I sadly won't have the time to go into. And so to analyze these sorts of things, you need complex lab equipment. This is equipment that cannot be flown on a spacecraft. Physically cannot. So for example, in this case, this is a synchrotron beamline, and right down here you can see the scale bar is a car. And so this is not only too large to fit into a payload of a spacecraft, but also too large to even make it to the launch pad. And in fact, the beamline is actually more expensive than an entire space mission. Furthermore, you have the flexibility to analyze samples and ask new questions. So for example, here's Jamie Elsela in my laboratory, and she is right now in this picture analyzing samples from one of the Apollo missions for amino acids for their stable isotopes. And this is answering questions about the origin of the amino acids, which was unanswerable because the technology had not yet been invented in the 1970s when the samples were collected. Incidentally, Jamie was not yet born when the samples were collected. So having this archive of sample return material that's been stored under good conditions and well documented enables this type of research. And so future scientists, maybe those not yet born, or maybe those in this audience, can ask questions that the researchers hadn't thought of when they designed the mission to go get a sample. So there's a history of sample return missions. The first one is actually Apollo 11, that returned the first extraterrestrial sample to the Earth on purpose, followed by other missions to the moon. The Genesis mission returned samples of solar wind. The Stardust mission returned samples from a comet tail. Our laboratory was actually luckily involved in detecting glycine, the first amino acid confirmed as a molecule from a comet. The remarkable Hayabusa and Hayabusa 2 missions, the upcoming MMX mission, and Mars sample return missions, as well as the Artemis sample return mission. But among these, I'll be focusing on the OSIRIS-REx mission, of which I'm a project scientist. OSIRIS-REx is a mission to an asteroid, primarily for questions of origins, to return and analyze a sample of pristine carbonaceous regolith. The sample comes back in just under 2 years from today, and is designed to collect surface material of at least 60 grams and as much as 2 kilograms. It also has the objective of spectral interpretation, the second 2 letters in the acronym. That is to provide ground truth for the telescopic data of the entire asteroid population. There's right now over 1 million asteroids that have been discovered. We cannot send a spacecraft to every single one of them. So by comparing the telescopic observations we get from Earth with a sample that we can see close up, we can then infer more about the total asteroid population. Resource identification is mapping the chemistry and mineralogy, also learning how to navigate around such a small object. This can actually be used for the emerging discipline of asteroid mining and space resource utilization. So we've actually made some progress in this, both not only by identifying the compounds or the chemistry of Bennu, but also learning how to navigate around such a tiny object. Security is measuring the Yarkovsky effect, which is this non-Keplerian force that has light, basically pressure, and re-radiation from the surface of Bennu, sort of like a light mill, but it's a somewhat different process, but it's reminiscent, that causes the asteroid to deflect its course a little bit over a long period of time. And Regolith Explorer, that is to document the regolith, the surface rocks and dirt at scales down to the sub-centimeter. And so there are a lot of asteroids. The Minor Planet Center today has 1.1 million asteroids detected, of which there are almost 27,000 near-Earth objects. So this is a top-down view of our solar system. Here's Jupiter, Mars, Earth, Venus, Mercury, and the Sun. And then these green objects are the main belt asteroids. These blue objects are the Trojan asteroids, actually the target of the upcoming Lucy mission, which will be launching next month to go tour them. And these red objects are the Earth crossing or near Earth asteroids. And so we had to pick an asteroid. And so at the time of mission formulation, there are only 500,000 asteroids known. We needed one that we could get to and back from in the lifespan of the science team. We want to actually see the results of what we started. So that led us down to, at the time, 7,000 Earth asteroids. Of those, we needed an asteroid that we could get to that has an orbit that, without so much of an inclination, that we can't use a rocket we can afford to get to. Of those, we needed an asteroid with a diameter greater than 200 meters. Smaller than this, the asteroid tends to spin up very quickly due to something called the Orp effect, which can spin up to as fast as 1 revolution per minute, which is bad for 2 reasons. One is the surface rocks and dirt that our sampler is designed to collect wouldn't be there; they'd fly off. And secondly, and in many ways more importantly, it's a huge navigation problem to basically dock with an object spinning that fast. Of those, only 5 at the time had spectra that told us those carbon rich. And of those, Bennu was the best characterized. The second best characterized, by the way, was Ryugu, the target of the Japanese Hayabusa 2 mission. Anyway, this was characterized with a wide range of ground and space-based objects. And actually, Arecibo data, as mixed with some goldstone, gave us the shape model, which turned out to be remarkably accurate. Of a half-kilometer across rotating asteroid, rotating retrograde, with a day of 4.3 hours. It's quite a walkable object, assuming that you were there and didn't fly off because of the low gravity or suffocate because of the lack of air. That it's sort of on the scale of walking around the Palace of Culture and Science, which I hope to visit someday. It's a spacecraft in many ways the same as any other spacecraft you've seen. It has solar arrays, a high-gain antenna. It has a science deck with a payload of instruments, but it has these other funny things. It has this up here, which is a sample return capsule that comes back to Earth. And this 3-meter-long pogo stick on the end of it is a sampling device, which is basically like a backwards air filter. We blow a jet of nitrogen gas into the surface. This is video from a microgravity flight we took on one of these Vomit Comet KC-135 flights. Inject gas into the surface that stirs up the regolith and gets trapped inside of this container. There's a little check valve on the bottom that keeps too much from coming back out again, and that holds the sample as the spacecraft backs away. And so the spacecraft is very well equipped with a suite of instruments, a spectrometer that can map the surface from 0.4 to 50 microns for 2 spectrometers, navigation camera that can also provide a little bit of science data, a suite of cameras which can view down to the subcentimeter as well as from great distances, a Canadian supplied laser rangefinder that has 2 different laser energies which map the surface in great detail topographically. Rexus was a student experiment from MIT and Harvard to map elemental abundances in X-rays, assuming that there was sufficient solar flares from the sun to enable it to do so. And of course, the usual radio science you can do with your various antennas back to the Earth receiving systems. I'll take a moment to also emphasize that because we're interested in the molecules of life, contamination is extremely important to both control and understand. And so I was in charge of putting together and helping implement a contamination control and contamination knowledge program, where we deployed contamination witness plates and analyzed those, both for performance as well as for requirements. We actually collected bits of the rocket fuel used on the spacecraft to analyze that. We deployed an additional set of contamination plates to monitor particles and films and have some of those archived for future scientists to study in case there's an anomaly that comes up in the sample. Likewise, we have an archive of all the materials that were on the spacecraft that had a reasonable pathway to get to the sample, as well as the various gases that we analyzed that were used in the purging the spacecraft and preparing it for flight, as well as, of course, the gases used to stimulate the surface in the sampler. And so this is a long process. This is a PI-led mission. The PI is Professor Dante Loretta, University of Arizona. And we started thinking about this mission in 2004. We're eventually selected in 2011. And if you don't know, when you win a spacecraft mission, NASA doesn't just dump a pile of money on your driveway. You actually go through many, many reviews. So we spent most of our time in this conference room arguing over different implementations, all the way up to CDR in 2014. So that's 10 years of PowerPoint and some minor experiments before we can actually start building a spacecraft. And I'm proud to say that OSIRIS-REx launched September 8th, 2016, on time and under budget. Spacecraft is more than just the hardware, it's the whole team. And this is a team photo right before launch. I'm down here in Project Science, but of course, as I mentioned, it's University of Arizona is the lead, with the participation from Canadian Space Agency, Arizona State, Harvard, MIT, Kinetics for navigation, University of Arizona for one of the cameras, and Goddard for one of the spectrometers, as well as, of course, mission management. So Bennu is a challenging object. We spent a lot of time studying it and doing rehearsals on how to collect the sample. At the time of sampling, October 20th, 2020, this was had a one-way light time of 18 and a half minutes. The sample was collected after a lot of practicing, and I'll tell you about, as well as understanding Bennu as an object. And so here is Bennu. It's like I said, half-kilometer across, roughly spherical asteroid that was remarkably similar to our predictions based on the Arecibo data. Surprisingly, it is a very similar shape to Ryugu, which is another carbonaceous asteroid, which was the target of JAXA's, Japanese Space Agency's Hayabusa 2 mission, which was very different from Itokawa, the target of Hayabusa, the also Japanese mission. So we had done a lot of our modeling based on what we knew about asteroids, looking at Itokawa, for example, and saw that there are these smooth terrains here, which would be very, very sampleable. And we knew it was round, so it should be very easy to navigate. But we were surprised. But I should say, before that, we had to get into a record-setting orbit. We actually got 2 Guinness Book of World Records for the closest orbit of the smallest object. So that's just kudos to our expert team of navigators. And so when we got to Bennu, we found out that it had a lot of boulders. This was a huge surprise because the Arecibo data said it was fairly smooth, except for one big boulder. And the thermal inertia, that is the change in temperature of the surface as the asteroid goes from day to night, night to day, said that it warmed up and cooled down like it was a sandy beach. And so having these big rocks was a surprise and rather terrifying because we had to find a place to collect the sample. But there were craters and enormous boulders with a huge range of albedo. From the majority of it is very, very low, 3 to 4%, with some rocks right here. This bright one that's much, much, much higher. In fact, these bright rocks look like they're pyroxene, and perhaps from vestoids, maybe from Vesta, or the source of the HUD objects. So it looks like we see rocks from other asteroids that have gotten mixed up into Bennu. We see a strong water band, very different from what they saw on Ryugu, with hydrated clay minerals and phyllosilicates and magnetite, which is another indication of strong aqueous activity. We found that our thermal inertia measurements from the ground were accurate, but our interpretation was totally wrong because of the rocks in Bennu look extremely porous, very fragile, such that they don't retain the heat as you expect a solid rock to do. They behave more like sand as far as their thermal inertia behavior. And so the biggest boulder has the lowest thermal inertia. And Nightingale was the place that we ended up selecting to get our sample. We also measured the Yorp spin rotation, and it is spinning up as was predicted, and does indicate that it is a loose rubble pile all the way through with interior voids even. And we measured the Yarkovsky effect change, that it changed 185 kilometers over the 12-year observing period since it was discovered in 1999. This actually means that we have a much better understanding of the impact probability of Bennu. Bennu is actually one of the most hazardously known objects, with depending on what happens on this encounter with the close past the Earth in September 2135, that there is a 1 in 2,700 chance of Bennu impacting the Earth in 2182, and a cumulative probability of 1 in 1,700 chance of impacts over 32 approaches in the 22nd through 24th centuries. So what this means is that depending on what happens on this encounter with the Earth in 2135, future scientists and engineers can make decisions with the data that they have from Bennu on if they need to and how to divert the orbit of Bennu to protect a potential impact of the Earth. So this is all great news for future us. We also discovered, much to our surprise, that Bennu is ejecting particles. These are a couple of centimeter-sized rocks that we see flying off of the surface of Bennu at different intervals in discrete events that end up either coming back to Bennu and making more arrays of rocks come off, orbiting for a brief period of time, or escaping. This was a huge surprise, and of course, initially was of great concern to the navigation, but it turned out that the rocks are small and moving slow enough that they weren't a hazard for the spacecraft. It was instead a boon for further understanding the gravity field of Bennu by tracking these objects. We also, when looking at the sampling site of that we call Nightingale, detected carbonates and organic material. And so this is great news because these are the samples that we're bringing back to Earth to study, including macro scale carbonate veins that perhaps indicative of huge hydrothermal systems on the ancient Bennu. Now, remind you that we had to do this all during a pandemic. The spacecraft arrived at Bennu in December 2018 and did most of its observations pre-pandemic, but the actual navigation to collect the sample was done all remotely, and this was an enormous challenge. To tag with Bennu, the spacecraft was in a close orbit and then diverted orbit to fly across the pole here, as you can see. We had already done this twice. This is actual all spacecraft data that's been put on this animation. We had done 2 rehearsals to a checkpoint and a match point where we stopped the rotation and target for a free fall for the last 25 meters until we touched the surface. It turned out that as I mentioned, the spacecraft was designed to sample on a sandy beach-like object with these wide areas of no boulders. These did not exist. And so while we designed the spacecraft to look at a 50-meter diameter landing ellipse, one did not exist. So we had to use spacecraft resources to come up with a new method that we'd had as a backup. Instead of using lidar to use the cameras to track the surface features, to choose this much smaller ellipse. This is a 10-meter diameter ellipse. And we targeted the center of this spot with our spacecraft, and autonomously, the spacecraft actually touched the center within 1 meter of that ellipse. So again, this was at 18.5 minutes light time. And so here are 3 camera views of the spacecraft descending to the surface. This is one of the SAMCAM looking right down. This is the red square looking down at the sampling device, and this is the navigation camera with this green square looking down at the sampling surface in the edge of this Nightingale region. You can see that the sampling arm is descending. Here's the shadow of the sampling arm coming down to touch the surface. And then contact, we blow the nitrogen gas. A plume of rocks come up, and then we fire the backway thrusters, and more rocks come up, and you can see the TAGSIM arm sticking out here. You can see its shadow. You can see the shadow of this plume of rocks excavated from the sampling site as the spacecraft motors back away and then get into a safe distance from the surface. And it should end right about now. And so we did an exercise to reconstruct what happened during this contact. So the spacecraft was descending to the surface at 10 centimeters per second. That's again this free fall from the last checkpoint to make sure that the engines didn't fire too close to the surface and potentially contaminate it with unburned hydrazine. The spacecraft contacts the surface, and then the spacecraft continues to sink into the surface for an additional up to 6 seconds before the gas fires. The gas fires, and the spacecraft is slowed down from 10 centimeters a second to 4 centimeters a second. So the action of the gas firing, which acts as sort of a thruster, as well as the surface properties of Bennu, barely slowed down the spacecraft. The spacecraft sank another 23 to 48 centimeters into the surface, totally burying the head, which is ideal for lifting sample. And then the thrusters fired, and the spacecraft backed away autonomously at 40 centimeters a second, as you just saw. The spacecraft was designed so that we could hold the TAGSIM head. Here's the bottom of it, of the sampling head, looking at it. And then we would spin the spacecraft around and measure the change in moment of inertia to see how much sample we actually recovered. Well, it turns out if you look in this picture, you can see there's a shadow here. And if you change the gain, you can see a few more shadows here. Those are rocks from the surface of Bennu that got jammed inside the TAGSIM head, propping open this mylar flap. The sampling head was so full of material that it was literally overflowing. This is actually a contingency we'd never seen on our testing on Earth. We'd never gotten this much sample in our testing. So the sample head was probably packed full of material, but sadly, these rocks jammed open the mylar flap, and some material was coming out. And so here, as we were taking images of it, we saw particles falling out of the TAGSIM head. I had nightmares thinking about each one of these particles as a PhD thesis not being written. And so it's crucial to skip the mass measurement and just get the TAGSIM head sealed as quickly as possible. So the head was placed inside of the sample return canister, locked in place with latches to secure it. You need a tug test to make sure it was really secure. You can see a few extra particles drifting out. And then we severed the arm to cut the head off and secured it. This actually leaves the TAGSIM arm sticking out of the side of the spacecraft in its still position with 2 full bottles of nitrogen gas, because we had prepared to do 3 sampling attempts if necessary. We had enough time and resources to go back and look at the sampling site. So here is this crater. Here is before sampling, and here's, you can see the sample spike is at this red X. And then there's a gouge dug out, and you can perhaps see some lines where the thruster plumes scoured the surface. And there's also this rock here that's like 3 meters across here that got thrown by this sampling event. So it's a very violent event. And Bennu is so loosely bound that the material was able to fly everywhere. And so we have the sample. It's safe and sound inside the sample return canister, headed back to Earth to land in 2 years from last week. And the science team will be able to test 25% of the sample to analyze, to answer these 12 hypotheses, as well as the 56 hypotheses that derive from them. Of these, hypothesis 2 is most concerned with astrobiology questions, looking at prebiotic organic compounds, as well as also astrobiology questions from understanding asteroid dynamics. and as well as a number of other things that are in these these sub hypotheses. But excitingly, 75% of the sample is not analyzed by the science team, but is available for future scientists. Perhaps you, perhaps your children, perhaps your grandchildren can come up with hypotheses that we haven't thought of, experiments that we haven't considered, and use them to analyze the sample in new and exciting ways. And so I'll remind you that the spacecraft is coming to Utah in September 24th, 2023. Just before 9 a.m. Mountain Daylight Time. We have a range of publications you can look at from the mission at asteroidmission.org, as well as more videos and things of that sort. And just to end with some stories, that during build and test of the mission, the first PI passed away soon after selection. There was Canadian austerity movement that grossly delayed one of the instruments. A U.S. government furlough. There was a fire that destroyed an instrument housing and its backup. There was a blizzard that delayed building a different instrument, the MIT instrument, and a train wreck that destroyed a piece of that instrument as it was being delivered to MIT. User quality control issues and detectors. There was even an explosion of a SpaceX rocket right here, about 1 kilometer from our spacecraft here, which was stacked on the rocket with a full solid rocket booster next to it. And the whole spacecraft shook. It was a very scary thing, but we were able to do testing and make sure that the spacecraft was in good condition and was able to launch on time. After launch, there was a nationwide internet edge that cut off the deep space network from the command center. And I was fortunate that we had a member of the navigation team who happened to be on vacation in Los Angeles for Christmas break, was able to bring the commands on a thumb drive to the deep space network to get the commands entered so that we could actually insert into that record-breaking orbit around Bennu. As I mentioned, the surface of Bennu was unexpectedly rocky. There was another government furlough, the unexpected particle ejections, another blizzard, and a global pandemic. With all of this, launch was on time and under budget. There was only a single safe mode during outbound cruise due to a mistake with the file formatting, but that had no impact on schedule performance, and no other safe mode since. One laser on the OLA instrument failed well after suspected life, and we're able to successfully recover from that. And sadly, the sun didn't cooperate by giving us good solar flares for Rexus. So I'd like to end by saying this is a remarkable team, and I appreciate your attention and your interest in this topic. Thank you.
Cool. Thank you so much, Jason. I mean, it's a really fascinating mission. The first of this kind, I mean, including, of course, also the Hayabusa 2 mission. But we are really looking forward to the results and to the outcomes. And we are really looking forward to the outcomes of your research. So let's go to the questions. And there were already several questions.
Wonderful.
On the chat. One of the first questions that we got is what kind of organics were found in ordinary chondrites, or maybe phrasing it even differently, what kind of organics you could find in ordinary chondrites?
So ordinary chondrites are organically poor. They have some polycyclic aromatic hydrocarbons and low levels of amino acids. For astrobiology, they're not all that interesting. My biased opinion says. Now, carbonaceous chondrites are a whole other matter. Those are rich with up to 3% organic material, of which most of that is these insoluble organic compounds. But the solubles have amino acids, they have sugars, they have polyols, they have carboxylic acids, nucleobases, sort of the stuff of life. And understanding how that got incorporated into life or helped get life going is a huge question. And the processes that made this could have been the same ones that happened on the early Earth, but I like them because I have access to these samples. I can literally hold them in my hand and hold a meteorite and study it. Not this one, obviously, because it's hopelessly contaminated with my fingerprints. But unlike the early Earth that has been subducted and lost. So it's a great indication of what chemistry is possible in the early solar system on Earth, or Enceladus, Europa, Mars, Ceres, your favorite object.
So actually following up on this, when we think about many organic molecules, including amino acids, which you mentioned, they are characterized by chirality, which simply means that they can exist in two forms, like two hands. And these forms are their mirror images. So I'm really curious. I mean, you study this as well, as you already mentioned, and then we also so from your website, so you're interested in chirality. So do you see any excesses of one or the other in the materials from meteorites that you work with?
Yes, that's a fascinating topic. Meteorites are one of the only examples of a natural abiotic system that shows a chiral excess. We see an L excess of certain amino acids. We see an L excess of isovaline, which is a rare amino acid in biology, not absent, but very rare, and is confirmed to be extraterrestrial by looking at its isotopic ratio in C13. It appears as if this L excess is correlated with the amount of aqueous alteration that the meteorite experienced. So ones that saw a lot of water tend to be amino acid depleted, but highly enriched in isovaline up to 30% or so. Ones which saw less water seem to be have no enrichment. I'll also point out that we've never seen a de-enrichment of any amino acid. It is how this enrichment happened and then how it got amplified is a huge question. And my favorite techniques is of crystallization of chiral compounds, which has been pioneered by our colleague Donna Blackman, that seems to correspond with the same sorts of amino acids that we see have this enrichment. But there's ongoing work in that area. I'll also point out that we've seen proteinaceous amino acids that have an L excess, glutamic acid and aspartic acid principally. And it takes a lot of work to determine that these are, in fact, indigenous to the meteorite, not contamination, because, of course, there's ready contamination of the L excess. That's, again, done isotopically and by looking at the other amino acids. So in the Aguas Arcas meteorite that landed in Costa Rica in 2019, and the Tagish Lake meteorite that landed in Canada on a frozen lake bed in 2000, we see excesses of these two diacid amino acids, but which are actually the same ones predicted by Blackman's work. But we see racemic serine and alanine, which are predicted not to be made excesses by Blackman's research. That's very interesting. But there's contamination is always a problem. And so that's why getting a sample back in a context you understand with witness plates to prove they don't have contamination from Bennu will be so valuable.
Mm-hmm. Yeah, I mean, that the findings that you just mentioned are really fascinating because I mean, also just to embed some of our listeners who are not chemists or maybe not biologists, the L amino acids are actually the ones which constitute biology.
Right.
So finding them in meteorites in this form, or at least some significant excesses of those, is really, I mean, remarkable. So I would be really...
It's both good news for astrobiology, but also bad news for exploration.
Yeah.
So that way, if you go to Mars and you see L amino acids, like, well, gee, does that mean there's life? Well, no, it could mean that there's meteorites, which we know that there are. But never having seen D amino acids maybe tells us something about the chemistry of life in the solar system, if not the universe. I'll also point out that there are polyols, such as you get in if you have a sugar acid, you can see L excess, D excess, same one you see in biology. In fact, even homochiral in the larger ones, which is really crazy. Sugars have not yet been measured this way, but the sugar acid, which are similar chemistry, have been. It's really fascinating, and we hope that samples from OSIRIS-REx will help us, or help you if that's your research.
And to follow up again, I was also wondering, I mean, you are probably really awaiting to get these samples. So what will you be mainly looking for in these samples from Bennu? Will those be amino acids? And actually, do you have any predictions what you could find, or even wishes what you would like to find there?
Well, so we have an international science team. So we're looking at amino acids, alcohols, bases, other nitrogen heterocycles, the insoluble organic material, the sugars and all the polyols, pretty much everything we can think of to look at. I'm hoping we see something like we saw in Tagish Lake, or so. Actually, what I really hope is something we've never expected, never seen before. But I can make predictions that it looks like this is a primitive hydrated sample, something like a CI meteorite. So maybe it'll look something like Orgay, but without the same level of contamination. We have all these hypotheses, but I'm really just hoping to be surprised. But whatever it is what nature's telling us. So I just can't wait to find out.
Fantastic. So I have a very interesting question about simulating space weathering of asteroids in a lab. So could you tell a bit more about it? What conditions can you simulate in a lab? How can you do it? And what acting sources of energy, I mean, thermal, mechanical, or radiation, what can you use?
So it's none. I don't do this research myself, but the people I talk to, they either use ion beams to simulate the flux of these particles that can create space weather. That is the alteration of surface materials by exposure to space, or they use fast lasers to simulate the impact heating of a micrometeorite hitting the surface. To understand that, mostly they use the lunar samples as a proxy, because we have the most space weathering from samples brought back from Apollo just by sheer mass. And so that's a very good place to compare against. There's a number of research groups doing that. My bias is astrobiology, and this isn't so important for me for astrobiology. So I can only give you hearsay about what I pick up at meetings and things of that sort. That's pretty much. Any more than I've said, it will be dangerous.
Yeah, exactly. But also sounds like an interesting aspect. But anyway,
indeed. Let me mention one other thing while I remember. Mm-hmm. You saw in the picture of when the spacecraft was looking at the sampling head and stuff was flying off. There are these round little discs. Those are stainless steel Velcro that we put on the bottom as sort of a backup sampling mechanism, and has a chance of actually sampling the very surface of Bennu, because that touched the surface first. And so we'll be looking at individual grains picked out of this Velcro for space weather material to see how that's different from the bulk sample. So the space weathering fans have a chance to look at interior versus exterior sample to maybe answer their questions.
Mm-hmm. Well, but yeah, that is also very interesting, because even thinking about amino acid excesses, you could have more on the surface or less excesses on the surface in terms of their chirality.
Oh, very much so. But you're sample limited, so these are individual grains.
Yes, yeah. Anyway, thinking about the two missions that were sent to these asteroids that you showed, we had Ryugu and Bennu, and actually they have a bit different timescales. Although, I mean, as you showed, it's very long term in terms of planning, and also it is a long term mission itself. But we already have the samples from Ryugu. So what were the differences in the initial assumptions and also goals between these two missions, which resulted in these different timescales?
So the missions were actually planned independently. And it was a lucky accident, I guess, that we had 2 spacecraft with different capabilities and different sampling strategies going to 2 different but perhaps related objects. The research on Ryugu samples is ongoing, and there will be a Hayabusa 2 symposium November, I think, where you can, it's a free online thing, you can register and learn more about that mission. The research is ongoing, and there are no results that are yet made public. I don't want to break my my oath of the rules of the road by disclosing anything out of turn. But the Hayabusa 2 mission collected 2 samples. Instead of using a gas jet, it used a tantalum bullet that it fired at the surface and blew material that splashed up into a cone that was collected into a chamber. Chamber would rotate and go back to the second surface, which was in the plume of an explosion that they made to sort of dig a crater and pull out material. They recovered well more than they ever planned, over 5 grams. They were hoping for hundreds of milligrams. They got 5.2 grams of sample. For Bennu, we were hoping for 60 grams. We got hundreds of grams. We forego the actual mass measurement, but all of our estimates say that there are probably many hundreds of grams. And so the samples are from different asteroids that have similar shapes but different spectral properties. Theirs is hydrated. Ours is Ryugu is not very hydrated. Bennu is very hydrated. It'll be fascinating to compare them. And in fact, the organics analysis team has dedicated a portion of the Bennu sample to take through the identical extraction methods used by the soluble organics team on Hayabusa 2 to compare it. So we'll have maybe we can have an apples to apples comparison, if you will.
That also sounds really exciting. I mean, comparing these 2 similar but actually different asteroids. And actually, we also have a question that is related to this. So one of our listeners asks whether we will ever come back to Bennu, or are there any other exciting asteroids that we should visit? And maybe you have some ideas about it. I know that you showed some future missions that are planned.
So, there are a million asteroids, and it'd be great to go to all of them. I don't know which ones will be the best ones to visit again. There is no plan right now to go back to Bennu, but perhaps it will be after the 2135 Earth close flyby. Perhaps someone else will come up with a mission concept to do so. The OSIRIS-REx spacecraft, after delivering the capsule to Earth in 2135, in 2023, will be in very good shape. The spacecraft is functioning extremely well. The instruments are in good shape. There's lots of fuel. And so the team is developing a concept to, after Earth flyby, to go to asteroid Apophis, which is one of these potential Earth intersecting asteroids, and do a rendezvous there. That's a proposal to be considered by NASA as a way to utilize this resource. It's one of these S-type asteroids, so very much like Itokawa, like an ordinary chondrite. So not a whole lot for organics, we believe, but we'll be sending up perhaps a fully capable spacecraft to measure that, and of course compare how Apophis has changed before and after its Earth flyby in this next decade.
And hopefully we will have samples from Mars if all works well.
Well, very much so. I'm excited about that. I'm part of the science integrity team to make sure that we get the best quality samples we have for the budget that exists. So I'm very excited about Mars sample return. And MMX, the Phobos sample return mission. And maybe someday a Comet nucleus sample return mission. I love sample return because I can ask questions I haven't thought of.
Yes, I mean, that is actually really exciting to have these pristine samples. So actually, speaking of those, you also worked with samples from the moon. So what differences are there between the samples that came back to us from the moon and the samples that you are expecting to come back to us in almost 2 years from now from Bennu? I mean, of course, this is a chondrite, a carbonaceous chondrite. So is there more organics or?
Tremendously more. The moon is profoundly organically depleted. We measured very trace levels of some amino acids, and most of those are associated with contamination. We are using those lessons to help formulate the contamination requirements for the Artemis mission, to bring back samples from the lunar South Pole. And we have an ongoing project called ANCSA, which is some acronym, which is looking at samples collected by the moon that have been stored under sealed under vacuum or frozen for 50 years, and seeing the differences between those samples and the ones that we've already recovered. But so we're looking for a whole suite of compounds: cyanide, amino acids, carboxylic acids, aldehydes, ketones, and comparing those. And the levels are extremely low because the moon is very low in volatiles, very low in carbon, water.
That is also, I mean, an interesting thought, because I never thought so much about it myself, but it's great to know these differences. Anyway, we have another interesting question, and that's about one of this of the slides. Ivan Paulo Lima writes, Jason mentioned in one of his slides that approaching of the spacecraft to Bennu was one-way light time of 1830. And I think we actually have 2 questions about it. So could you tell a bit more about it?
Oh,
or
sure. So that's jargon I should have defined. The solar system is big, and the speed of light is relatively slow compared to this enormous size. So you may have heard about the one-way light time between the Earth and the Sun is 8 minutes. So if there's a solar flare on the Sun, you won't see it for 8 minutes after that happens. When you look at a star, it's however many years old based on its number of light years away it is. So the one-way light time, it means that the spacecraft is 18 and a half minutes, 18 and a half light minutes from Earth. As that means you send a command to Bennu, it takes 18 and a half minutes to get that command there. Which is why you pre-program the spacecraft to do its operations. You don't drive it with a joystick, because there's an 18.5 minute lag.
Which is pretty much the same problem that we have with the rovers which are sent to Mars. Exactly,
and depending on where Mars is or where Bennu is, that time changes.
We also have a question, which is an interesting question in terms of thinking about alternative biologies, which could develop maybe somewhere in the solar system, we still don't know, or maybe outside of it. So I think it's more of a teasing thought. Would not the best outcome be finding large excesses of some D-amino acids or, for example, L-ribose?
That'd be great. That would tell us, that'd be a really good evidence of both a second genesis, perhaps, on Mars or wherever, independent of biology on Earth, and be a very clear not contamination. Seeing a small polymer of amino acids that are D would be amazing. It would have kind of protection implications. You have to think about whether or not that could be potentially hazardous to terrestrial biology or terrestrial ecosystems. We have to do that no matter what, but that would be Nobel-winning research. That'd be fundamentally change our understanding of biology. That would be the best outcome. Yes.
Great. And we also have a question about your working routine, and I guess we could ask it in two ways, especially, I mean, working routine during the pandemic, because on one hand, it definitely affected the control of the mission, and on the other hand, it actually really affected the way your lab works. So could you tell us a bit more how you are handling this in your lab, and how these challenges of the pandemic were overcome during the control of the mission?
Yeah, so it's been very challenging. During mission implementation, I was used to traveling to Denver, where the spacecraft operations center is, or to Tucson, Arizona, where the science operations center is, once or twice a month. And traveling under normal circumstances, I'd probably give this talk live and enjoy visiting beautiful Warsaw, which I hope to do at some point. In that respect, it's been bad for my frequent flyer miles, but it's been good for my sanity and my sleep. That I don't travel nearly as much, and that's actually better for my carbon footprint. But so we've been doing a lot more virtual meetings. I haven't been on an airplane for a long time. We do things remotely, routinely now. It makes it more difficult to make sure that the minority voice is heard, and you can't see expressions as well. It's much more complicated and much more challenging to do not face to face. There are some operations that are so critical we send out a couple people, but not the usual large contingent of people who are there just in case. I'm more of the just in case person. Project scientist tries to think of groupthink, try and help explain the science to the engineers, explain the engineering to the scientists. That's less crucial at some of these operations when we just have to get something done. So I can listen from home and do that. I work at a NASA center, which is a gated complex. And so there's a security guard who makes sure that if you're on center, you're supposed to be there. You can't just pop in your lab and do something. So we're capped at 25% access as of about a year ago. Before then, it was 0% allowed on center. And so the people who, I'm an old man, so I stay at home and I write papers and review things. The people who are actually doing the science, they're in the lab. Only one person per room or two people per large room. They're masked all the time, and they can get the highest priority research done, things that have urgent deadlines that are mission critical. So like our research on Hayabusa 2 samples, that's high priority. Our research on looking for compounds and peptides and new species in new meteorites that fall, that's low priority. So that has to wait. And that's unfortunate, but health and safety of the personnel is more important than pushing back the frontiers of astrobiology, I'm sad to say.
I mean, exactly. That health and safety is here the most important issue. But I mean, actually, speaking of the lab and the way you work, many group leaders still are tempted to come back to the lab at some point and maybe do some experiments. So how about you? Are you one of those?
Not really. I go in when I have to. So I'm one of the few people who is actually decent with the torch. And so when we have to seal tubes under vacuum for certain experiments, I go in and I take care of that work. One of our processes involves using hydrazine. I know how to do that distillation, so I take care of all of that work. So that means I go into lab once every month or two for a day. And I try to go at times when no one else is around, except for, of course, lab safety to make sure that someone can hear me if there's a spill or something of that sort. Making sure that especially the young people in my laboratory are safe and have a long career ahead of them, that they have enough to keep their careers going and enough to keep their health going is more important than whatever I want. And at this NASA center, this lab is a consortium of many PIs. I've been there the longest, so I formally direct the lab. but we have very talented other scientists who are independent scientists in their own right. We pool resources, we pool space. And so it's all about balancing our needs, our families, our mental health, and our physical health. So we try and have an enlightened view of it. And if a discovery has to get postponed, it has to get postponed.
Yeah, I mean, especially during these times, it's been very difficult. So, I mean, there is also a lot of admiration from us towards your work and the way you can handle it. And we are really, really happy that it can still move on. And I mean, once again, looking forward to the results of your studies on the samples from Bennu.
Absolutely. And I'll also encourage your audience to write proposals to get the sample. It'll be released to the scientific community 6 months after sample return. There'll be a catalog, and you can request samples as you would any other mission sample.
Which is also a fantastic opportunity. I mean, everyone from the world can actually apply for it and possibly do some experiments.
That's right.
Wonderful. Thank you so much, Jason. Our time is coming to an end. It's been wonderful to listen to you speaking about the mission and about your research and also your plans to study these samples. I would also like to thank you, all of our listeners who joined us today. Thank you for your time. And remember, there is a possibility to join the networking event on the Hopin platform, and we are also having the poster session today, so you can speak to the poster presenters on the chat and also upvote the posters. So have fun. There will be more of it tomorrow, and thank you so much, Jason, once again.
Thank you for having me. Enjoy your conference.